the Verifiable Computing Project, or how do we build trusted and open source hardware. So this is the talk outline that I have planned for you all today. What we will not talk about is computer architecture, or things like how do we design, processors, pipelining, that sort of thing. I will not be covering that. I will also not be covering like the basics of digital design, and I will not be covering things like VLSI or floor planning and things like that. Although there'll be some elements of that, I will do my best to explain what is actually going on. All right. So why should we even care about building computers that are verifiable? So as you can see, what these devices here have, servers in the data center, you have your iPhone, and programmable logic controllers in industrial applications. What do these devices have in common? They're all computers. They all have a processor, memory, and all that sort of thing, right? Like all in those, all in just different form factors, different packages. So depending on who you are, you might be asking different questions about your hardware. How, like if you're an end user, you may ask, how do I know that the device I use are trustworthy? Like for example, if I say that, hey, I'm doing something sensitive, I'm a journalist or whatever. If I put my phone into airplane mode, how can I trust that it's actually in airplane mode, that it's not sending anything, to any other source, that the radio is not actually turned on, but the operating system report it's off. And down even to a lower level, right? How do I know that if I send design, let's say I'm chip design, I send my design to a fab, right? How do I know that the chips I get back from a fab are exactly as I designed and they're not tampered with? We'll actually look at, two real examples, right, of these things from, these categories. In fact, at the moment, we are actually dealing with a case when iPhone was actually compromised, and somehow or other, stalkerware got installed on this iPhone. And the facts of the case is that we know this phone to be compromised because the adversary actually messaged one of my contacts. He also happens to be here this afternoon with things that we were saying on the live Zoom call. Police forensics were not able to find the point of entry, like how that stalkerware even got on the phone in the first place. And they were not able to find any traces of stalkerware. The phone, and mind you, this is an iPhone, right? iPhones are regarded as poor. And the owner didn't jailbreak this thing. How did that software get into, the iPhone in such a manner that it could conceal itself? It could not be detected by, the owner of the phone. And I mean, the point I'm trying to make also is that a lot of consumer devices might as well be black boxes to their owners. We have all these devices, but yet we do not really know what's actually running on these devices, what consists of the tech stack, like what your operating system is, what the firmware is, and so on and so forth. We do not really understand our devices. Okay, so a second example. This is a very simple CMOS inverter. If you've done anything, with digital electronics, this is one of the simplest logic gates you can build. So you have a PMOS transistor on top and an NMOS transistor on the bottom. So the idea is that, the way the PMOS works is that if the gate voltage, which is at input A here, the gate voltage is below a certain threshold, the transistor is on. In the NMOS transistor works the opposite way. If the voltage at the gate exceeds a certain threshold, it turns on. So let's consider the when A is actually 1. What happens? This NMOS transistor actually gets turned on, and what happens is that it effectively sinks all the current from VDD to ground. So the output logic is 0, and vice versa. So here is implementation on a chip, right? A sample implementation on a chip of an inverter. Try spotting the difference though. The two of them, there is a difference. It's just very difficult. If you're still having trouble actually finding it, that's the point. What I am presenting here is a dopant level Trojan. That means we do not alter the fundamentals, layers of the chip itself. All we do is that we alter the doping concentration in, this, you can see this part of the layer is N-type. Is it? No, it's P-type and it's supposed to be N-type. And this area is N-type and it's supposed to be P-type dope. But see, ion implantation, doping, is a very precise process. Doping is a process of changing these electrical properties of a semiconductor by introducing dopant atoms like boron or phosphorus. So in that manner, you actually change how the actual base silicon itself conducts, and by building layers, or what's that? By building and doping various layers of silicon and things like that, you can actually build transistors. But in this case, what has happened here is that this Trojan inverter, right, no matter what the input, it's been doped in such a way that no matter what the input is, it will always give you a 1. The circuit will always be on. So basically, it doesn't matter what the input is, it will always be on. But this is just a very simple example, because what I'm trying to show you here is that the structure, the fundamental structure itself, like where your contacts are and where the metal layers, how the metal layer is structured, has not fundamentally changed. So another real-world example. This is the Intel Ivy Bridge random number generator design. So you have a source entropy, and the two main things that we want to focus on are the conditional and the rate matcher. So you have a source entropy that feeds in conditional, and the conditional will then feed this rate matcher, right? Some random number C in certain intervals when it thinks that, okay, it's, there's enough entropy, right? We can generate a seed, right? So in the rate matcher, what we do is that we actually do a doping level attack on the rate matching part of the circuit, and I'll explain how this works. Okay, so the idea is this. So what you do is that you generate two things. You have two registers, C and K, and these actually are your seeds for AES. But this is AES counter mode, right? So you have your state register K and C that are supposed to be random, but C, as you can see here, is super random, but you increment every time, right? You increment every time, and these two seeds they'll get fed into a circuit that gives you a random number output. But we can do something. We can actually do this thing, right? Remember that NOT gate attack, right? I can also apply that NOT gate attack on flip-flops, so that the flip-flop states are always fixed and always determined. So in this attack, what we do is that we modify the flip-flops, right, that make register K, so that they always give you a constant value. And on the state register C, we modify such that some of the bits, right, are also always constant. So what happens is that what you have done here is you've actually made the random number generator not so random. And the fun thing here is it still passes Intel's built-in self-test. And this is how the researchers in this collaboration between universities, this is how they implemented that Trojan, right, in silicon. And they didn't even change the structures, mind you. Again, we do not change the structures of the chip at all. We only change the doping type or concentration. So, as you can see, based on what if you read the paper, what it says is that, well, I've taken a 128-bit number and I've made it such that so a 128-bit number is actually a very long number and it's very difficult to prove false. But if I can make those numbers that are generated more predictable, right, I can actually effectively shorten that number of bits down for 128 effective bits, right, less. And the attacker actually gets to decide how many bits, right, what is and therefore the probability of them actually guessing the random number that's generated, which is often used in cryptographic applications. So, in doing so, right, your messages, your messages or your communications from, your computer to website and so on and so forth, they may not be as secure as you think if a chip is tampered this way. And you see, what makes this tough is that unless you know that this attack has happened, right, you have no idea what you're looking out for. You have no idea what you even. And as the paper has already shown, by choosing how the attacker sets their constants, right, in random number generator, we can also defeat Intel's built-in self-test. And while the built-in self-test still works to detect manufacturing defect and so on, it cannot detect that the Trojan actually exists. You have no idea that it's there, unless you know that that's exactly what you're looking at. And here's the thing, because it's doping level attacks, the fact that iron formation is so precise, you're talking about one doping atom, one dopant atom, in 100,000 silicon atoms, right? There's no way, even with scanning electron microscopy, for you to see it because the structure looks more or less the same. The only way you can detect this is if you compare your production chips with a golden chip. But then, again, how do you know that the golden chip hasn't been tampered? There's no way for you to verify. Because it's very difficult to inspect the fab process, right? Fab processes are very closed off. A lot of them, there are a lot of proprietary process tooling, process equipment, things like that. And so it's very difficult to actually inspect. And as I said, it's hard to know that a chip is even tampered unless you really have a sense of something. You're looking for it and you're building tests for it. Unfortunately, there's no open source chip fabrication process. And right now, work is still being done in that space. There are a whole bunch of hobbyists, hackers, and things like that. We're actually working on. They're working on actually figuring out how to build their own open source process tooling for chip fabrication, things like that. But that's still inaccessible for most of us. So what can we do for now? And we can actually prove that, at least to ourselves, right, to our users of our devices, that yes, this device is clean, that we can verify, and the user can verify for themselves that the device is clean. And as I said, this is a slight digression. The folks have actually been working on, their own DIY chip fabrication, open source chip fabrication process. And actually Sam Zaloof especially has got down to quite an impressive level. As you can see, 10 micrometer feature sizes, and I believe that one of these arrays has 1,000 of these transistors that you see right here. And he's done it all in his garage. So now, for the demonstration that I have, we are using FPGAs. But why use FPGA? Well, it's a general purpose device, and they are used in so many different applications that it's very difficult to predict which batch of FPGAs will go into which company or which product and things like that. So it's very difficult to tamper in silicon. And because FPGAs are programmed with a hardware description language, HDL, the user can actually look at that code and say, hey, I know how this processor works. I can see that code for myself. I can understand how the processor and everything else in my device works. And they can customize it. They can change the operation if they wanted to. They can hack around it. And okay, so now that I mentioned FPGAs, not everyone here may be familiar with FPGAs. So so general structure of FPGA, just look at it. You have a whole bunch of configurable logic blocks that are connected by switch matrix. And at the pins of your FPGA, you have your I/O blocks. So let's look at one. So this is how it looks. How it looks like. The internal block diagram looks like for a lattice ICE40 FPGA. So you have a whole bunch of programmable logic blocks, which are connected by a interconnect, and you have 4 I/O banks. And inside each of these programmable logic blocks, you have these lookup tables that can be configured for for any digital logic function. So you can say that I want to implement with a bunch of logic cells and implement a certain digital electronic function. I can do that because your software just configures the lookup table here. Of course, you can configure it such that this device is a synchronous device, so I have a clock input. I want to have an enable input. I can configure that. Each logic cell is very configurable in that way. And the I/O bank and I/O cell looks more or less like this. And based on how these, I will assume multiplexers are set, you can set the pin as an input, output, or high impedance output, or tri-state output in digital electronics. So there are already existing works in this field, which is the most well-known one is Money Studio's precursor, which is supposed to be a RISC-V development kit. So this is how, you see, the thing is that when you implement the processor on FPGA, you actually get to inspect it. And he actually gives you the entire circuit, right? And you can actually, and not just a circuit, you can actually see how the processor is implemented on the FPGA. You actually also can see that. So you can actually, if you really wanted to, take the time to verify and understand how the system on chip and how its internal peripherals, blocks, and so on and so forth work. So now we get to talk about before I even get to talk about FPGA tools and the tool chains, let's talk about the design flow of for FPGA. So you create your HDL, and it goes through like this process. You create the RTL, you synthesize, you create a netlist, you do your implementation, which just basically translate, do the mapping, you do place and root, and you do your timing simulation. And once all that is done, and once the timing, everything is verified to be correct, you generate a bit stream, which is then programmed into the FPGA. So synthesis. So let's talk about these processes. Synthesis is basically the process of taking your hardware-registered language code in Verilog or VHDL and converting it into a netlist file that describes logical connections between blocks. So in FPGA, you may not just have your configurable logic blocks, face lock loops, other RAM blocks and so on and so forth. Synthesis creates a netlist file that describes the logical connection between these blocks. Place and root basically says, okay, I'm going to take this synthesized process, I'll turn it into a physical implementation based on the FPGA device. So if we have a given FPGA device, we say, okay, we know how many logic blocks we have, or logic cells we have, we know how many PLLs we have, so on. So we do the place and root. The place and root software will figure out what's the best way, right, to place or to configure which logic blocks on the chip so that the design is actually efficient. And you're not just so you don't have something like, oh, I have these elements on one side of the chip, but my other elements are all the way on very long routes like that. So that's what the place and root is supposed to take care of. And finally, we have bit stream generation. So at the end of the synthesis and place and root processes, you need to generate a bit stream file that can be programmed into the FPGA. And what's that? That bit stream basically is just a configuration file that programs all of your logic blocks and other blocks, right, to do what you meant them to do. So this is just the general 3 steps, right, of of FPGA design flow. And they're actually processed too. So Yoast is actually an open source tool. In fact, all these tools are open source. Place and root, you have Next PNR. And bitstream generation, you have various projects under F4PGA. And we get into F4PGA itself. F4PGA aims to be like the GNU compiler collection, right? But for FPGAs. And it's open source FPGA toolchain, but with a focus on FPGA architecture and its definitions, right? So how, like the bitstream generation process itself for various devices. And so far they have been able to make open source tools, right, for the Xilinx 7 series, the Lattice ICE40, ECP5, and QuickLogic. So what you have your synthesis here. Your synthesis tool is mainly use this, and you have FPGA tool. So Project iStorm actually and so on. Those are the tools, right? The bitstream generation tools for the specific FPGA device that you're using. And of course, there are other tools for verification testing. And F4PGA currently supports, as these 4 FPGA families, right? Although to varying degrees. As you can see, for Project X-Ray, it's targeted at Xilinx 7 series, right? They haven't really nailed down how to do DSPs here, certain blocks here. So there's still a lot of work in this domain that has to be done. So for my demo, I use specifically a tool chain called LightX, which is a framework for building specifically systems on chips. And you can take, for example, a pre-configured, I want a RISC-V core or some sort of 64-bit, right? And I say, I want, Ethernet, I want PCIe and so on. I configure all of that, right, in my design, my system on chip. And it uses MyGen, which is actually a Python-based HDL. So it's more familiar to people who come from software engineering background. People who have been doing Verilog or VHDL system Verilog. So you have, what's that? So this is how LightX is actually organized. So it's based on MyGen, as I said. And the build tools are, you can use this on open source, but of course it supports the manufacturer toolchain, so on. And they have other cores, right, like for Ethernet or for video, that sort of thing. And at the moment in 2018, they supported 21 boards. Right now the number is much higher, but I was not able to find the flow chart, right? The updated flow chart for this, so I'm using older. So the board I have here is Acorn CLE15, and in LightX, they actually support this board, and you can actually come up with your own system on chip. So in this case, in the example, they have a VEX RISC-V CPU, which is a 32-bit RISC-V CPU. They have a UART, and you can even put in SATA support, so you can plug in a hard drive or solid-state drive, although I have not configured it for this demonstration. And as you can see with LightX, this is actually all in Python. You can see, user LEDs, right? What pin, what is the, what's IO standard or IO voltage, right? You can define where the connections go, what resistor is that. So we sort of actually talked about RISC-V, but why RISC-V? Why do these toolchains, especially LightX, support a whole bunch of various RISC-V cores? Because RISC-V is an open source instruction set architecture, and it's actually so small to the point that you only need less than 50 instructions to implement a full RISC-V 32-bit integer instruction set. And at the moment, actually since 2020, I believe, the base and standard instructions have been frozen. So that's not going to change at all. So if you wanted to extend on it, you want to add your own accelerators instead of instructions, right? You can actually extend it yourself. You can actually write your own IP, or your own core, and you can extend your RISC-V core. And as I said, this is all you need. These are instructions that you need to implement RISC-V 32-bit integer instruction set. So as I said, I'm using, in this case for the implementation, I'm using an Acorn CLE 215, which is interesting because these used to be FPGA miners, so they use currency mining and things like that. But crypto mining with FPGAs have become unprofitable. So these things have been going for cheap. Sometimes they're even less than $20 US, that sort of thing. And this is, the block diagram of the devices, the device itself and things like that. So you have RTX 7, actually 7A, 200T. And for the price, like, $120 US, right? It's interesting. Because what you're effectively getting is the highest end RTX 7 in this module right here with 200,000 logic cells. This is the highest spec part on the RTX 7 series family they can get. And in the office, I actually did the same thing. Set up the development PC and got it. So the demonstration is actually kind of strong. But this, as you can see, is a 64-bit Rocket RISC-V core. And what's that? There's no operating system. Yeah, I didn't have to build, a working Linux system. But as you can see, what we have done here is that we actually synthesized a whole processor, right, onto FPGA. And we actually can customize that processor using LightHack and things like that. So yeah, I mean, in the BIOS itself, the Linux BIOS itself has some, like memory tests and so on. Even the serial have the Linux image, or to do so. But yeah, so this is pretty much the demo. The thing is now a RISC-V computer. So I'm actually working on two main projects for the future. One is a laptop based on this. I'll be extending build a laptop that's based, for which is processed RISC-V processor in FPGA. And it's pretty much, the goals for that is similar, or what we're trying to achieve is similar to the precursor project from Bunny Studios, right? In the precursor, it's more like a development kit. So, it's mainly aimed at hackers and things like that. Want to mess around with a RISC-V, open source RISC-V platform. And it's very customizable and things like that. But in this case, I want to focus on, okay, so you have these RISC-V cores, right? Can we do general purpose compute? Can I synthesize a processor on FPGA that, I'm not even aiming, of course, you're not expecting things like, i7, i5 sort of speeds, right? But if you can even get it to Raspberry Pi 2 sort of speed, what's that for, for FPGA, and not even like a custom ASIC, right, for FPGA, that's actually pretty fast already, if you can even get it to that level. And the Airwave project is just an extension of that. It's basically investigation of phone security, but from the perspective of the baseband processor, which is part of your phone that actually talks to the cell tower. So we are actually looking at implementing our own baseband processor on FPGA, and then it talks like RF transceiver. So the whole thing is software-defined radio. And on the Airwave project file, I've also been messing around with post-market OS, and possibly, because I'm actually looking at RISC-V, possibly we might be able to get a port for RISC-V working. And okay, these are the references and resources that I've referred to slide. Yeah, you can find me on these, and you can come find me and talk to me on these platforms, and my email and things like that. Questions?
Sorry, let me pass you the mic.
Can you implement the same verifiable computing methodologies you've done in SCADA? Because when this can be air gap systems, but you don't know what's happening in the PLCs.
I do not see why not, right? I think I think there are probably other considerations you have to take note of, because it's an industrial device, and those sorts of applications may be used in situations where serious injury may occur. So as long as you do you do your homework and you know what you're doing in that domain, I don't see why not. I mean, there's also actually a RISC-V 32-bit E. There's actually more for I want to call, but it's mainly for microcontroller applications. So there's actually a whole specification for that.
Thanks.
Mr. Stepp, in your description, the bitstream generation, were you successful in using an open source bitstream generator for this prototype, or are you not there yet?
In this case, I'm using LightX, and LightX uses the Vivado tools itself. So I'm not using an open source.
How far are you from being able to use the open source bitstream generator for that purpose?
I think it's just a matter of configuring it. In this case, I admit this demo was actually quite rushed, so I did not go to the step of trying to do the bitstream generation, open source tools. But I think it might be possible.
Your expectation is that the currently unsupported features are not required for getting the RISC-V core onto the FPGA?
If I remember correctly, let's see. The blocks they are not.
It's the hard block.
So yeah,
DSP.
I'm actually not sure. You have to look at the documentation of what specifically mean. What I have seen is that people have been able to synthesize their own RISC-V cores on 7 series FPGA, and even on parts that the key packs are much more expensive parts. But I've actually not personally had the time to look into the exact specifics of that, how to get that tool chain set up and things like that.
So, okay.
Hi, I'm a software person, so not so familiar with these hardware things. I actually don't really understand what when you mention verifiable, how is it different from software defined?
Okay, so when we say verifiable, actually there are two ways to look at it. One, you can talk about software itself, and the software being open source, and you know how the software works. The second part of it, we do not see yet, is basically hardware itself, the implementation of hardware that is verifiable. Of course, one way to make hardware verifiable is if you could come out with an open source chip fabrication process and things like that, and you can do a process where anyone can just walk in anytime and say, I want to look at your process and I want to see how you're making chips and so on. But at the moment, that's not exactly a thing. And even the Sky 130 open source PDKs are not even at that level yet. It's just that the cells themselves, the standard cells for building the chips, right, are open source, but the processors themselves are not. You can't just walk and see, okay, I want to know how this chip works. I want to see how this chip is fabricated. I want to know your process and things like that. I want to verify that process itself. So on one hand, you have the software, the hardware, and what we are doing here is saying we are trying to verify down to the processor level itself. And at the moment, the best way about it that we have is by implementing the hardware itself on FPGA and actually peering into the hardware description language code, right, for your processors or whatever cores that you may be using.
Okay, so I'm actually, to be honest, I also from like a software background, so I guess maybe might summarize. Maybe I from what I understand, if I try my best based on my understanding, I guess what she meant, Joyce here is trying to say is maybe like FPGA is like you can like you program like logic gates, right? Something like that. Yeah. So at the oh, okay.
So it's a bit similar to how you code. So you can actually see the code, like your hardware description language code itself, and how everything comes together, right? Like how the core itself is built in that hardware description language. So it's closer, a little bit closer, but not exactly like software development. But it's in the sense that, okay, if let's say I want to know how this device works, I can just download the HDL software myself. I can look into those software and verify in the process that maybe it could be say some a bit similar to how you would verify software, how it works and so on and so forth.
So it feels like the approach we are taking is to have a white box process to build one hardware that we think it does what we think it should be, instead of taking a black box produced hardware and checking if it works correctly.
Yes, and what's that? To do that, let's say we look at an off-the-shelf chip. Is as I said, like previous slide, even if let's say a chip is tempered, if you're looking at tempering at the dopant level, right? Even with scanning electron microscope, it can be very difficult to detect or see because with doping level attacks, you don't actually change the physical structure of the chip itself, only the electrical characteristics of the transistor on the chip. So how then can you know that the chip has been tampered with? It's very difficult and it's very expensive. A lot of some of these processes are actually destructive. So in order to figure out how that chip was fabricated, you actually destroy the chip itself. And that's not something that is accessible for most end users. One of the focuses I have here for the Verifiable Computing Project is actually asking a question. As an end user, if I wanted to verify how my device works, can I do that? And what sort of tests and what sort of things can I run to convince myself that the hardware is indeed doing what it's supposed to do and is clean?
Hello? Yeah. My name is Chun Wei. I'm a computer engineering graduate, so I know a bit. I really see it very difficult to imagine that ESP can approach Raspberry Pi performance anytime soon. Have you investigated doing like a CPU in lockstep, or at least you have two CPUs from different vendors? Then at a certain state you compare the state and check whether the results are the same. Would that be a better and a more promising approach for verifiable computing?
Maybe, but I'm going to ask you this question, right? So from a user's perspective, so let's say I bought this hardware. How do I know that the hardware actually works in a way that I expect it to do? What sort of tests can I do, right? And what you describe is basically saying that I'm using this hardware.
Yeah, from different vendors.
From different vendors to verify. But then the question I ask again, right, is even let's say I go to another fab and I make a golden chip. How do I know that process or that golden chip hasn't been tampered with?
Yeah.
So
if it's tampered, then they will agree.
What's that? So the thing is that it's very difficult for you to know. At with the current chip fabrication process, at some point you have to implicitly trust that this process is not as likely to have been tampered. And so, and then I can use this, right, this chip or these set of chips as a reference there to all my other production devices. Yeah, that's the thing. You also really
Yeah.
can't.
Randomness cannot be trusted. Yes, probably have the external rules.
So yeah. So again, so what I'm doing in terms of verifying, of course, you're right. The FPGA are likely not going to, at least the lower end FPGAs are not going to reach Raspberry Pi speeds, right? If you try on things like that. So I'm trying to look into that and see that, okay, I'm going, let's say I have a RTX 7, this is the highest end RTX 7 you get, and Kintex 7, or even a Kintex Ultra Scale, or other better device, right? What sort of performance am I willing to, price ratio, right? Am I willing to trade off to reach the goal of actually making hardware that's general purpose, is performant enough to do most applications, right? Most things, but yet doesn't break your bank too much. At the moment, I've just set it that the default is 100 meg. I've not changed. I've not tried to clock or change the core speed, right? More than that.
Joyce will still be around after this.